What we're slowly doing is we're connecting what we did in algebra to what we're going to do in calculus. We're defining the pieces we need to define the integral and differential parts of calculus. What we talked about last time, we talked about instantaneous and average rate of change. We're going to continue from that today. All right. So, average rate of change. How does it relate to the secant line? What's the relationship between there? What is the secant line? Anybody know what a secant line is? Yes. No, it's a line that has a slope. A secant line, let's say a circle. We're going to do a lot of circles today. A secant line cuts through a curve at 2 points. That's a secant line. And of course, since it is a line, it has a slope. But that's a secant line. That's what we're looking at here. But now the reason being we use the average rate of change with secant lines, because for the average rate of change, you need to have 2 points. You can only take average if you have two numbers, and that's what's happening here. And basically the slope is delta y over delta x. It's the average rate of change. We just started, so you're not too far behind. Oh. So let's now, because we're also going to start defining terms that we're going to use to define calculus. And we're going to look at how something approaches something else. What does that mean? We're going to look at how, when you differentiate, what does that mean? So we're going to introduce some of the terms today. So for the average rate of change, secant line, delta y is y2 minus y1. Using function notation, y2 is the function at x2 minus the function at x1. Again, this is just algebra review. Delta x is the difference in the horizontal axis, the x2 minus x1, which is also how we define h, because the h is going to be the pinnacle part. As we can see here in the definition, the average rate of change of our function f of x with respect to x over an interval x2 and x1 is written this way. Delta y over delta x is y2 minus y1 over x2 minus x1. That's algebra. Then we go into the difference quotient, because now from the average rate of change where you have 2 points, we want to know what is the rate of change. What is the slope at 1 point only? The only way we can figure that out is by finding the slope of the line tangent to it at that 1 point. And that's what we're doing here. Because you notice here we have 2 points. We have x1, x2, we have y1, y2. So we have 2 points. And here, all we have is the x value at 1 point and the function at that point. So we're looking at here, right now, we're saying that h cannot equal 0. But how do we get the instantaneous rate of change? How do you think we can get the instantaneous, from the average rate of change, how do we get the instantaneous rate of change? Not setting h to 0. That's what if we set h equals 0, then we have 0 at the bottom and we fail the basic function of mathematics. To obtain the instantaneous rate of change, from the average rate of change, we find the values as h goes to 0. Eventually, you're right. Eventually, we'll get to the point where h is 0, like we did earlier in the examples yesterday. But we're more interested what happens as h approaches 0. Because we're gonna find out that there are three things that can occur that don't really have to exist for a value to exist. But there are three different possibilities that can exist. So this is what we're looking at. This is the symbol we'll be using a lot. What this one says, as h approaches 0. That's how you read that. So how would you define the slope at a point on a curve? If you had to define a slope of a curve at one point, how would you do it?
The point slope form.
Because remember, we only have one point. Well, we can't use really the point slope form because that requires x1, x2. Right here, because it has to do with this. We can find if we had 2 points, point 1 and point 2, we can find the average rate of change. The average rate of change is the slope. And that's of the secant line. But what we're looking for 1 point is we want to know the slope of the tangent line. That's what we're looking for. Well, that's it. Yeah, that's what eventually that's what slope. We're using m as slope for all lines. But the difference here, this is where it gets difficult, is we don't have 2 points. We have to now rewrite our equation so that we only have 1 point. And how does it behave as it approaches that point? And we're going to do a couple examples. If I give you a graph, you can't really just look at the slope of that 1 point. What you have to do is you have to do just this. You have to take different values, the slopes of different points, the secant lines at different values as it approaches that 1 point. Or so if I want to know what is the slope of this line here, of that point there, what I would do is I'd start off with this one. I'd find the slope of that one. Then I would get closer and find the slope of this one. Then I'd go in for closer. I'd find the slope of that one. And then I get even closer. And then even closer. Because what we're doing here, even though we may not get the actual value, but we're getting to a value that's approaching the true value. So that's, and you'll be faced with some homework assignments. So I'll give you a graph. It says, find me or approximate the value of the slope of that curve at that point. And that's what you have to do. You have to take a whole bunch of these other ones and see where is it approaching. Ideally, in mathematics, we look at them from both ways. We look at from the left and from the right and see how these behave. And then eventually they're going to meet the same point. And if you do that, then you have the true slope of the curve at that point. That's if you use iterative methods in computers and programs. Put your phone away. All right, so let's look at an example here. Well, let's just go jump to an example. Find the slope of the tangent line to the parabola y equals x squared at the point 2, 4. By analyzing the slopes of the secant lines through 2, 4. So how do we do this? How do we start off doing this? We know our function. Our function's what? X squared. What's the graph going to look like to begin with? We know what the graph's going to look like. It's a parabola. It's x squared. So find the secant. How will we find the slope of the secant line to that curve at that point, to that point? Because what we have to do in order to find the slope of the curve at that point, what do we need? We need to find a whole bunch of these other points on the curve and then find the slopes between each of those. So let's begin with the first one. What formula are we going to use? Which one? Okay, so what do we start off with? We're going to start off with delta y over delta x. X plus h squared minus f of x over h. Why is it f of x plus h squared? Because it's the function squared, right? So for our equation, since we start off, this is our x one, we have 2 plus h squared minus 2 squared over h. Let's do the FOIL first. So we have 2 plus h squared, which is 2 plus h times 2 plus h. 2 times 2 is 4. 2 times h is 2h. 2 times h is 2h. And then h times h is x squared. So it's 4 plus 4h plus h squared. That's this first part. Bless you. Simplify, the force cancel. So we have 4h plus h squared over h. We can factor out an h on top. 4 plus h. Oh, I'm sorry. So we get the value 4 plus h. What does that represent for us? What does this equation represent for us? Okay, keep on going. It's safe to say everything we do in this chapter will deal with slope. So that's a safe answer. But more precisely, what? Which one? Yeah, yes. It is the slope, but what kind of slope? Slope of what? Yes, it's a slope of the secant line through 0.24. We start off with the 0.24, and what this gives us, for any h that we pick, we now have the slope for any h we pick. So however far value h we have, we plug it in there, and that'll tell us our slope. It'll decrease it. So the bigger it becomes, the more steep vertical becomes. The closer it goes to 0, the closer we get to the actual slope at that point is 2. So that's what we're looking at here. So as h approaches 0, what do we get? Our slope becomes 4. Because that's what we're looking at that point. That's another example. Oh, so these are secant lines. What's the difference between secant and tangent? I mean, a secant and secant and tangent over there. How would you define the difference between those two? What's that? Yes. So it makes it what? Because remember the terms we used when we talked about our slope. With secant lines, we used average rate of change. Now with tangent lines, what do we use? Instantaneous. Rates of change. Why is that? I mean, if you think about it, it's a no joke. Why are both of these defined the way they are? Exactly. Secant is through 2 points. Tangent is at 1 and only 1 point. So with the secant, I can take the average of the 2 points. With the tangent, I only have one value, so it's instantaneous at that point. Again, it's once you look at it, it's a no-brainer. Example 4. Here we have to use this graph. I'm sorry, but they already catch up. I got to show you a graph. Here, I'll read it out to you. Figure 2.5 shows how a population of fruit flies, Drosophilus, grows in a 50-day experiment. The number of flies was encountered at regular intervals and counted values plotted with respect to the number of elapsed days t, and the points joined by a smooth curve. And here we go. So these are over a 50-day period how many fruit flies we have. What's also a side note, this curve is pretty much true for any biological event. You look at pandemics, you look at influenza, you look at anything like that, has the same curve. As time goes on, very few people are sick. All of a sudden, more people get sick. All of a sudden, there's a time where everybody's getting sick. And then why does it taper off? What's that? Yes, true on both of those cases. On the worst case scenarios, yes. It's either immunity or death, or what's another thing? How many people are there? Eventually, you saturated the market. You can't infect anybody because everybody's infected already. So what happens there? It drops down dramatically. So that's exactly what happened with the COVID. That's the same thing that happened with the malaria and all these other diseases that are floating around nowadays. So what I'm looking at here, it's asking, find the average growth rate from days 23 to 45. Find the average growth rate from days 23 to 45. How would you do that? It says average, doesn't it? So we're looking for what kind of graph? Secant. So what formula do we use? The average, the f of x2 minus f of x1 over x2 minus x1. So let's go ahead and do that. Determine the value for me. What's the average growth rate? So tell me how many flies are growing per day? And yes, you're going to use your calculators for this because I don't want you guys to break your heads.
8.6, right?
How'd you get that?
Does it look good?
Yes. Now, how did you get it?
I divided 190.
How'd you get 190? Again, you're in a calculus class.
Yeah.
You're in the real world. You're not going to say, it's right there. No. I say, how did you get it? That's it.
340.
So the rest of y'all, how'd you get it? What did you put in there? What's the first number? Minus x2 is x1. Right. You plug those values in your calculator and you'll get 8.6. Again, that's average rate of change. The same thing. How would we do? What if I want to know the instantaneous rate of change on day 23? How would you do that? Yes, but your H would be 0. You wouldn't get anywhere. What you would do is just take that value and take it any further. You can't do that. That'd be the first logical choice, but you can't do that. What you have to do, remember, when we go to instantaneous, we're looking for the instantaneous rate of change at that point there. As H goes to 0. Whenever we deal with instantaneous, we have our formula f of x plus h minus f of x over h. We're looking as h goes to 0. What happens? So what this is telling us is we have our first secant line. Then we do the next one. We would do that secant line. Find that slope. This is slope 1. This is slope 2. Then we do the third one. This is slope 3. Then we get closer and closer and closer. That's the only way you can truly guesstimate what the instantaneous rate of change is of an object, of a curve. You have to take the surrounding points, and as h, as your distance goes to 0, you're seeing what value does that approach. So we know that at this one, we know it's 8.6. What's this one going to be at this point? We calculate that one. Is it going to be higher or lower?
It'll be lower.
It's going to be higher. Why? Because what's happening to the slope is getting more
Oh.
steep. Eventually, when we get to this point, it's going to be a lot more steep. So what we have to do is we have to find the slopes of the secant lines infinitely as we get closer to 0. This is the part you'll have when you do your homework problems. It's going to give you a graph and say, okay, find the instantaneous rate of change at this point here. The only way you can do it is by taking this sequence of secant lines and approximate what is it getting close to. Now, if we had the true function, if we had f of x, then we can calculate that much more readily. But since we have a graph, we're stuck with what can we read from the graph. What is this location here? At 40, it's at what? 340, 345, 330? Again, everybody may have a different number there, but it's going to be pretty close. We'll say that this is 340. And then we have this one. It's bigger than 250. Is it 260 or is it 255 at this point here? So you see what I'm saying is the choice, the X values you pick will determine on how accurate your values are going to become. But it's still going to approach a specific value. Right? And that I can't do anything but apologize because they didn't give you the function. They just give you a graph. And you have to find all these secant lines, the slopes of them. And that's just a very painful process. Which is why I'm not going to do it. It's very painful.
I noticed in our homework, I think number 8 was like that too.
Yeah, I'll give you a short. This is what it's going to look like. You're going to pick these values. You're going to find the slopes. If you notice, the closer we get to our value, the numbers are getting larger. Why are they getting larger? Because the slopes are getting more steep. So that's the way you have to do it. Yes.
This find the slope of one point right next to our original point. So like
You-
it's 23, 150, you got 24, 151. That's like the same. And that's like close to the same.
You could, but how can you? There's no actual validity to it because you're just taking one shot and that you guess that's it. With this, we see a pattern forming because that's what this is doing for saying we have to see what is the pattern going, and then 2, how close do you want to get to it? When we get to 22, because this is 25 here, do we go to 21? What is that value up here? Again, how accurate is your number going to be? But the closer we get with these other points, which is why if we had the actual function of that, it would make life much easier for us. Any questions so far? So that I have to apologize is that it's going to be very painful for you because it's going to take a lot of time to go do it. All right, so that's it for section 1. We're laying the foundation